As we know, reconfiguration times impact heavily on the final solution latency. Therefore, we may be interested not only in trying to hide the reconfiguration, but also in trying to maximize the reuse of reconfigurable modules. Now, maximizing the reuse of reconfigurable modules can be seen as a partitioning problem given a graph used to represent the specification or the algorithm we have to implement. Not only, detecting regular patterns from the designer's specification is a promising approach to find an interesting solution to the partitioning problem for a configurable architecture. The detection of repeated structures, in fact, allow us to identify reconfigurable functional units that are reusable, thus saving reconfiguration time. This extraction of regular structures from a given graph is actually a valuable step in different contexts, ranging from software engineering, as an example in detecting duplicate code both for plagiarism detection and for optimization purposes, to other areas such as VLSI design. Within this context, it is easy to see how the extraction of regularity from a given specification is an approach holding great potential in the definition of a design flow for a configurable architecture. Striving to reuse the reconfigurable functional unit, we identify is a promising way to lessen the impact of reconfiguration times on performance of the overall system. In this figure, we can see a possible output of the tree-shaped subgraph approach. This approach identifies recurrent structures, called templates, repeated in specification, and the goal of the algorithm is the covering of the input graph by utilizing instances of the tree-shaped templates, where a tree-shaped template is a template characterized by having a single output and within which each of the nodes has a single output as well. This is just an example, but don't worry, if interested, more examples and details will be presented in other classes, and I will also point you out to some interesting papers. As an example of how this procedure for template identification works, we can consider the proposed figure. Note that the figure is intentionally incomplete. As an example, it does not show all the generated templates for the sake of clarity. Colors are used to identify repeated structures templates. Therefore, nodes or groups of nodes colored with the same color are identifying a template. Once the template's identification is carried out, we need to choose the ones that have to be used to cover the input graph, to have the final set of modules that will be used to implement our system, and by doing this, we have also to decide how to use them. As an example, we can design a function which represents the fitness a template has when being implemented as one of the configurable units. Examples of a heuristic used for template choices include choosing the largest templates in terms of hardware area used, for the so-called largest fit first LFF heuristic, or privileging the templates that recur more often in the most frequent fit MFF heuristic. The winning template, according to the chosen heuristic, is extracted, and its instances removed from the graph. The choice is repeated on the remaining templates in the part of the graph still to be covered, until there are no more available templates to choose from. In this example, we can see 3 templates. The first one is made of 4 nodes and it has 2 instances. The second one is made of 3 nodes and it has been also identified 2 times in the graph, while the third one is composed by 3 nodes, but it has just 1 instance.